Thank you for the kind invitation. I'm going to first figure out how to share the screen. Please request recording permission from the meeting host. Okay. Share screen. Okay, maybe it's already working. Let me try. Okay, let me try. Can you see my
Perfect.
screen? Okay, great. Yes. Well, thank you, Julie, for inviting me to the Python Heliophysics Community Telecon. And here I will talk about the tool that I wrote together with our team at the center, at the Netherlands Center for Mathematics and Computer Science, CWI. And this is also, I'm also a first author on the paper that we submitted that accompanies this tool. And the whole idea is to enable, to make a reproducible data set, and so also facilitate reproducibility from machine learning experiments, because that stems from the data. And so this is a pipeline that sits on top of the DRMS and SunPy Fido functionalities. And then this allows, and then this pipeline allows further functionality in terms of tailoring it to user-specific needs, in terms of querying a specific cadence of products. And I will specifically speak about the SOHO mission. So the Solar and Heliophysics Observatory mission. In principle, this pipeline can also be used to query the SDO, but there are perfectly developed tools from the SunPy community which allow that as well. I included the SDO mission as part of this for completion. But the main motivation for this pipeline was because at least the JSOC, so there are two databases. Let me go here. So this is a schematic of the standardization pipeline. We're going to return to this image or the schematic a bit later. First, after this, I'll talk about the raw products and how they look like, and then from the SOHO mission. And then I'll go through, and I've included paragraphs. So it's going to be a bit of text, but I'm going to not verbally say all the text, but just highlight the important parts from these two steps as it's described in the paper. So the paper is here. So it's the archive paper that I've linked here. And also this is the GitHub page in case anyone wants more details, and also to actually clone the repo. And also, there are accompanying Jupyter notebooks as well. So one can execute Jupyter notebooks with deep convolutional neural networks and check out how this works for predicting in the user case that we give is BZ 3 to 5 days ahead of time of when the SOHO images are taken. So this schematic here, it includes two major steps. So the first is the generating the data, and the second is to synchronize the data. And in this trapezoid box, the green box on top. So basically there are two missions that are included, the SOHO mission, and I'll focus on that today, and also the SDO. And from the SOHO mission, as everyone knows, there are 7 data products, 4 extreme ultraviolet images, known as the EIT, 171 at 171 angstroms, 195, 284, and 304 angstroms. And also the Lascaux coronagraph images, the C2 and the C3. And there's also the MDI, which is the magnetic field mapper. That's the MDI 96M. 96M stands for the cadence of 96 minutes. And so this is the main script, the mission data generate.py. And then basically there are 2 branches here, and that's because one branch goes into querying the NASA Virtual Solar Observatory SDAC database, and the other branch goes into the Stanford JSOC database. And it used to be that the MDI images, so the magnetic field maps from the SOHO mission, would be sitting in, would be located at the NASA VSO SDAC database. But toward the completion of this pipeline, they were moved to JSOC. And so now SOHO MDI joins SDO HMI, which is the successor, the SDO successor of MDI, with much higher resolution and also higher cadence. and as well as SDO AIA, which is the successor of the EIT from the SOHO mission. So this pipeline allows the user to enter the start and end dates, also the time sampling rates. So let's say every 6 hours or every 12 hours or what have you. What fits best for the given task. Also, there are 4 different resize strategies that are given. So just regular subsampling, interpolation, and then min pooling and max pooling. So there could be different cases where each of these strategies might be used instead of the other one. And then, for instance, the target dimension. So what output size would one like? For instance, the natural size of images for the SOHO mission is 1K by 1K. And for instance, maybe for machine learning experiments, one wants to have sort of reduced image sizes. So maybe one wants to work with 128 by 128 pixel sized images. Also, the metadata is, of course, very important. And so here we provide also an option of including the metadata. And I'll get into an extra step that has to be done, because if one uses the native SunPy Fido functionality of including the metadata, that takes quite a long time per image, so around 15 minutes per image for MDI. And so I wrote an additional script, which instead of doing 10 to 15 minutes per image, it actually takes 10 to 15 minutes just for all 15,000 images, and basically retroactively seeds the metadata for the good images, for the images that have been pre-processed. And so also there's an email registration that's required, and that's required by JSOC. So before actually using this pipeline to query images from JSOC, one has to register their email with JSOC. And so there are these 2 branches, and I'll get into that in a bit more details a little bit later. But the main important thing is that after this main workings of this pipeline, there are HDF5 data cubes that are produced per image product. And they're also pre-processed. So any missing telemetry, any holes in the data or other kinds of missing data, we'll see examples of this in a few slides. That's removed, and the next time step based on the user input cadence per product is the image that comes next. And then these are all assembled together and then in an HDF5 data cube with the metadata that's been JSON serialized. And also a CSV file with the dates timestamps included, as well as a CSV file along with each HDF5 data cube. So that's the output of the step 1. And step 2 is the synchronization step, because for machine learning, one wants to have all the data products as close as possible in time. So basically for a given timestamp. And in this part of the pipeline, that's done. And again, producing the synchronized HDF5 data cubes per product, but now with the timestamp that's synced across different products, along with the CSV files again. And also based on discussions with one author that we consulted, or rather one scientist in Paris that we consulted, who is the PI of the EIT instruments. He suggested also that to include accrued F-corona subtracted products. And in the paper, we also tried machine learning experiments with this F-corona subtracted products. So that's a separate set of HDF5 synchronized data cubes, along with their accompanying CSV files that's produced upon running the synchronization step. So basically, SOHO has a very long baseline, so 25 years in running. And really very many images. So like here it says 50 terabytes of data in the SOHO archive. And I recall a figure when I first started of around 600,000 images that I was looking at initially before pre-processing. And this is how the products look like, ideally, with, these are the complete images. And so one has these extreme ultraviolet images, the EIT, at 4 different wavelengths. 3 of them are shown in this schematic. Then the 2 Lascaux images, and then the Michelson Doppler imager, the MDI, and they're shown here. And as you see right away, that there are different cadences to each of these images, and that makes it necessary to have a tool that synchronizes this in time after the images have been pre-processed. And so here it just says again that the native size of all these images are 1K by 1K pixels. And these are just intrinsic data. So for further information, for instance, these are the iron lines that are measured for the EIT. and also the helium line as well, and then also the data range at which these products are available. In the paper, I recommend, from my experience, to start with 1999 rather than 96 and earlier, or rather than earlier than 1999, because there are still different intensities of images. There are some non-uniform lighting conditions and so forth. So I would recommend working with images starting at 1999 for all these products. So this is examples of missing data, as I alluded to a bit earlier. So for MDI, one sees often these stripes, and these kinds of whole or missing data morphologies affect about 5% of the data in my experience. And so one has these stripes, these holes, and then these sort of tire tracks, especially in the LASCO images. And also there are planetary transits that occur, especially, exclusively really, or especially for the LASCO chronographs. And they can be seen as these bright horizontal stripes in the image. And so these are also removed, and there's a huge transform that's used in order to detect these. And then these images, either with planetary transits or with missing telemetry data, they're not used. And so the very next available image that satisfies the user's input, and as well as the quality that's desired, is the image that is then assembled into the HDF5 data cube. So these are the file descriptions. So so MDI used to reside on SDAC, and then it was moved to JSOC. And each of these Soho products, it comes at, different resolutions as well. So the EI2195 is notably also at 512 by 512 pixels. And these are the good resolutions, meaning that if one just goes and manually inspects the virtual solar observatory, one will find each of these products available at different sizes. And these if these sizes are different from these, then those images, in my experience, are not good to work with. Actually, they're kind of they don't really fit the bill of what one wants to use for later on for a machine learning system. Also, the file size is also important, actually, and especially when using the SunPy Fido part. And it's important. So the pipeline checks for the file sizes that are given here, because there are, again, a lot of different file sizes available, and those either correspond to self-calibration movies or images that are not squares, but rather elongated rectangles or other kinds of images, just stripes. So these file sizes, in my experience, having combed through the VSO database and inspected all these products and all the different images and resolutions, these are the ones that work best, or should be, or I should say, should be used rather than other ones. And there are different calibration levels as well. And now the MDI, as it resides on JSOC, it has the highest level, at least when writing this paper, which was level 1.8.2. And in the pipeline, there are also options to work with the coronagraphs that are also at processing level 1 rather than 0.5. But we recommend in the paper actually to work with 0.5 images because there are some, let's say, transformations applied to data in level 1, which could, which we believe with other authors do affect the integrity of the raw data, and that might not be the desired input. However, we do provide this as an option, so one could in fact query level 1. We just don't recommend it from our perspective. So looking at 10 years of data, so looking at, for the data that we used in the paper, we looked at January 1st, 1999 to end of the year, December 31st, 2010. And in this data range, we found, the number of files that were processed that were deemed good based on these criteria were around 15,500 MDI files, and also the same kind of order of magnitude, so around 10,000 to 15,000 files for each of these 7 products. And the HDF files, the cubes are not that large, so the largest there are half a gigabyte, but also just a few 100 megabytes. And then, as one can see, like the number of files that actually had missing data, so these holes, I refer to them just with the nomenclature of holes, or had planetary, and in parentheses had planetary transits, it's yes, significance for, let's say, if looking at EIT 171, there were roughly 10% of the data had missing data in it from the EIT 171 data. And for instance, looking at the LASCO, C2 and C3, in parentheses, the number of planetary transits, so files that could not be used if one wants to not use the images with planetary transits, then there were quite a lot, so around 24,000. So that's like basically around twice, a bit less than twice the number of actually good LASCO C3 files. So that's significant. And there are entire, it could be a month or two where one has these, let's say, Mercury transiting or Venus transiting. But even then, this is, we believe, better than simply excluding, let's say, simply instead of, so we believe doing this is still better than just excluding those 2 months. Because even if those 2 months, let's say, are computed that there is a planetary transit during that time, there are still some days where the images are not affected. So there is still good data in that time period, although that, let's say, a block of 2 months could be listed as a period of planetary transits. So returning to the pipeline again, so now I'm going to go a bit in detail, and bear with me, please. I apologize. I've copied paragraphs and pasted them in from the paper. I'll try to just skim them, so please don't read all the text that will be there. Before I do that, this is how it looks like in terms of actually cloning the Git repository and then actually running this locally. So executing this with a Python command. So basically, the script that one would run is entitled mission data _ gen.py, and these are the different flags that are available. So I've already described these inputs that the user can enter, and they're listed here. So these are all flags that can be used, and indeed, like the level 1 last call flag is there asking if if a user wants to use level 1 or not. Here it's important to note that one can, let's say, run one product or all 7 products from the SOHO mission, or the same, let's say, 1 or all 12 products from the SDO mission. But the missions cannot be mixed. So one cannot run products from the SOHO mission simultaneously as running products from the SDO mission. So these missions are just kept separate in this pipeline. And an example, let's say, inputs that one would use with the flags is on the right. So here it's like, the flag products. One can just either have spaces or not, and then list all 7 products or just a few. The data start, data finish, image size output, so the 128 going from 1K by 1K to 128 by 128. Here a time window selected of 6 hours, so this is in hours. One could put 12 or 24. Also, let's say the kind of resize strategies. So here just subsampling the image, whether to include the FITS headers as performed by SunPyFido. And for MDI, one would not want to do that, but one would want to run this other script, which I'll talk about briefly. But for non-MDI images, this FITS header should be set to Y, so to yes. So those run very quickly. And then just outputting, so specifying the mission and also the user's real email, because that's required for JSOC, and then just outputting it to a log file for references, because the log file will contain all, and with URL links as well, to all images that had missing data, and as well as planetary transits, so one could check, let's say, or just if one wants to refer back to those images somehow, they're good for bookkeeping. So that's would all be output to the log file. So data preparation. So as already we discussed, we'll run through this a bit fast. So one can either select SOHO or the SDO mission, and just run one, run the other one. Let's say, or run, products with different subsampling strategies. So run this pipeline with MDI subsample, then decide, hey, I want to run this on LASCO, but I want to do min pooling instead. That's all possible, just it has to be run separately. So one after the other. Also, here, one has the different products that are accessible, and then with the Roman numerals 1 through 4, just describing the different strategies for resizing. So the max pull and min pull use the block reduce function from scikit image. Yes, so we can go here. So basically, all the images that are queried are all in FITS format. And FITS format is the preferred format for this pipeline. We work with FITS images because these are scalar images. So for machine learning purposes, we don't need to worry about the RGB channels, but we can just work with one channel. So that's why we initially opted to locate images that were FITS, that were scalar valued images. Yes, so one needs to, so there are these compliant SunPy keywords in JSOC. And I already mentioned this level 1 and level 0.5 for the LASCO images. And these are the reasons that we believe that it's better to work with level 0.5 LASCO images. So I won't go through these various reasons. And then the necessity of including the email when using JSOC. And so now we come to the databases that are queried. So the Soho MDI or SDO mission products are in Stanford's JSOC database, and that's queried using their DRMS export rather than their DRMS query, because the query lists these ghost files which are of size 0. And that becomes troublesome. And so it's better because so this querying gives these files, but then when exporting doesn't pick up any 0 sized files. So there's a mismatch there. And so it's better to work with export, and that's DRMS export, and that's what's used under the hood in the pipeline. And so these are the series that are used for JSOC. So these level 1.8.2 for Soho MDI, and that has a cadence of every 96 minutes, and then the HMI. So then the HMI is already from the SDO mission, and that's every 720 seconds, and so forth. These are the intrinsic references to these various products from DRMS. And then SunPy Fido is used to query the rest of the Soho products, so the EIT and the LASCO. SunPy Fido, it queries NASA's VSO SDAC database. And instead of using SunPy Fido's native download, which times out after several thousand hits, I believe it could be, I think it's 10,000 hits, it'll time out. So we recommend, and what's implemented under the hood here is to use the wget function, and that avoids this timeout issue. Also, internally, because of this 10K results quota, there is also sort of an upper limit to the number of days in advance that one can span at a given time step. So this time step is just marching along. Let's say one inputs 10 years of data. So 60 days is the upper bound on how what the stride should be in marching through these 10 years, let's say, because of this 10K results quota. So this 60 days is hard coded in, and it also works perfectly with SDAC and also with DRMS. This DRMS has a 100 gigabyte export limit, and the 60 days is what is set under the hood in order to allow for a seamless run. So without any interruptions, unless there's a timeout on the database side. That's also taken care of, because if there is, for some unforeseen reason, the pipeline has not encountered any kind of breakages. If for some reason there is a break and the user notices that the pipeline has stopped downloading, let's say, a given product on a given day, it's all that's necessary to do is just run the flags again, but then as an input start date to put that date on which was the last date of the last product that was downloaded. And the pipeline is smart because it will check the folder and check the latest product that is there, and then seamlessly continue with the cadence, making sure that the time step the user inputs, so the cadence, is matched perfectly. So it will run as if there was no interruption. So it'll perform that check if there is an interruption. So this is inbuilt into the pipeline. And actually, the queries are singleton queries. So that allows us to not be limited by this 10K results quota, because each time that we're arriving at the index that corresponds to a given image, then this image is then downloaded, and then when this is locally downloaded, it's checked for its integrity. So only when the file size is correct, only when the other things that we noted are correct, it's downloaded, and then it's checked for this planetary transits, or it's checked for missing data. And if the data is missing, it's then erased automatically from the user's laptop or desktop. And then the next image, then the index is recalibrated again. And then the next images are continuing to be downloaded again with these local checks for image integrity. So yes, right. So this is, yeah, there's also a URL that's provided as well in case one wants to look at what images were skipped over due to missing data or planetary transits. Yes, and that's what I mentioned with the user can restart from last fits file date downloaded. So yes, so this HDF5 format, this hierarchical data format, that's what the HDF5 files are, and one has these data cubes pair product along with the CSV, and then we get to, so this concludes the data generation step, and of course, as we saw in the beginning, each of the products has a different natural cadence, and so it's important then to synchronize them across time, and this synchronization step will result in slightly fewer images, because the more products that one synchronizes, of course, naturally there will be less of these products available together at a given time stamp. So all 7 products, there will be fewer of them, of each product. If one wants to synchronize across all 7, then there would be if one wants to synchronize across 3 products or just 1 product. So then this is we start the data synchronization step. But before that, I had alluded to using this retroactive metadata seeding script. And that's because when querying with JSOC, it takes at least 15 minutes per FITS file. And that's not doable, because that would simply take weeks. So here, this just takes 10 to 15 minutes to run over all like 15,000 files. And what it does is it basically queries based on the dates that were received. It queries again the database and basically retrieves, these several keywords that we want to keep as metadata. So that
hey,
this process runs. Yes.
Just a quick couple minutes warning before we need to switch to the next topic, by the way.
Sure. Yep, I'm approaching. So this is the time synchronization step, and basically it synchronizes the data, and it inputs these previous steps, HDF5 cubes, CSV files, and then it looks basically half the time window ahead and half the time window below. That gives you the range for the synchronization time step. And basically, one also has as output these F corona subtracted files, and the way that's so it's a crude representation for the F corona. Basically, one looks at up to 24 hours before a given timestamp, so a given image, and then it subtracts that from that image to remove the F corona. And so basically the advantages of using this software framework are that it provides a standardized machine learning ready data set that can be used for space weather. It provides clean and temporally synced data. It's flexible and modular, so if one wants to add on other functionalities, it's very easy to, or query different databases or different missions. That's also possible. This is an open sourced code, and it's potentially a valuable resource for the community. And so there's also a data. So in this synchronization step, one can either generate from the first step these HDF5 data cubes and then use those as input, or if one doesn't want to run that part of the code, one can download from, let's say, Surfsara, or this data will be available, I think, from Zenodo as well. One can simply download the data and just use that, let's say, and if one wants to synchronize it, because that data would be at every 2 hours, what's available online for 10 years. So if one wants to use that data, but then synchronize it every 12 hours, one can. So then one doesn't need to run the first step of the pipeline. Yes. So then these are the data records. So there's like, just one. So one product, so MDI only for 10 years. So that's around 16,000 files. Then 3 products together that are synchronized. in time, and then all 7 Soho products that are synchronized in time, with and without the fcorona. Yeah, and that concludes my presentation. Thank you. Stop sharing.
Thanks, Carl.
The screen. Right. I hope I've stopped sharing the screen.
You
Okay.
have.
Yeah.
Thank
Okay.
you.
Thank you.
Does anyone have any questions for Carl before we move on?
We also might have time for questions for both if there's time after
True.
Jenny's talk.
Yeah, I'm going to be
Definitely.
pretty short, but I do have questions, but I don't know. I've never been to this group before, but I guess I can ask some questions. So yeah, Carl, that was really interesting. And I guess you talked about using it for other data products as well, but it seems like it's pretty Soho and SDO specific. Is that not true? But you mean other products from those missions, or?
Oh, thank you for your question. I don't see your name. Sorry, I missed it.
Oh,
Jenny.
my name's Jenny. Yeah.
Yes, Jenny. Okay.
And I'm not a scientist either, so I'm just asking out of curiosity here. So.
Oh, it's a great question. No, actually, you're absolutely right. So it's so all products from both missions are there. I think there are 12 products from SDO and 7 products from Soho, and I've been emphasizing Soho. What I indeed mean is that one can add on, I think, missions that are described in SunPy-Fido, or missions or other databases. So there are other databases to which SunPy-Fido can query besides the SDAC database. So one can, it's quite straightforward, I think, to add this functionality. I think, yes, it depends on the SunPy-Fido tool and on DRMS. If DRMS and SunPy-Fido can also query newer missions or other older missions, then that's also possible. So because, yeah, the code, the pipeline that I wrote, it sits on top of SunPy-Fido and DRMS functionality. And with allowing a user to tailor their queries in greater depth, because in my experience using SunPy-Fido or DRMS, I didn't see, or I wanted to have this finer control of the products, and these knobs I needed to add myself. Perhaps given that it's been over a year, or will be a year soon, perhaps this functionality has already been added. So because it's also a dynamic programming environment. So yeah, but at least in this time range, yeah, or maybe the developers of SunPy-Fido might look at the pipeline and just borrow snippets of code which are applicable, and then make SunPy-Fido even more robust or more fine-tuned.
And then have you looked at potentially putting this in the cloud in some sort of data environment, like I don't know, we have at Space Weather Track, we're developing this model staging platform where you do the analysis in the cloud so you don't incur all the costs. So I don't know if this pipeline was available in a cloud environment like that, that would be potentially useful.
Okay, like, so if I interpret correctly, like for me, more in the cloud environment, I immediately think about, like, let's say running machine learning experiments in the cloud, or let's say storing large amounts of data in the cloud. Here, let's say the data, it is only, it fits within the Zenodo 50 gigabyte limit. I think it's something like around 10 gigabytes in total for the 10 years, let's say, so that the user can just download that data. The machine learning experiments are in executable Jupyter notebooks that are on my GitHub. The pipeline itself just, well, basically takes, it's on the GitHub. I didn't include that chart, but on my laptop, it took, I think 5 hours for MDI, like 4 hours for other products. And basically there is no, like, I don't know how to interpret cost here. How do you mean, like, cost?
Oh, right. I guess data, I don't work in the cloud, so I'm not totally aware, but I guess as I understand it as data egress, like when you take data out, it's expensive. So if you were going to download it from the cloud, that would be expensive. But if you did your processing in the cloud and got your results in the cloud, that would be free, basically. And then generating the data in the cloud would also be efficient and could be stored there, and all the different versions could be there for people to use without cost, if that makes sense. as long as they can put their model code in the cloud. But this whole pipeline, like the way I understand it is you can have, data processing pipelines in the cloud that, bring in the data, and that's not very expensive, I guess. But anyway, I just was curious if there was plans. I don't understand it really well myself.
Plans.
But yeah. Yes, there are.
There are plans. There's a thing we're calling Helio Cloud, which
Nice.
Brian Thomas is the lead on. And we are currently gathering data as we speak. SDO and MMS are two initial ones, but this set could be a good one too. But the idea is to have tools, have the usual too many words in the language now anymore. So anyway, there are tools to work with the data and keep it close, and you can then bring in your own data and use that in addition. And there's lots of different possibilities. Jupyter notebooks, which I was thinking of. So all that's there and being spun up as we speak.
In Helio Cloud with Brian. Okay, cool.
Yeah, right. So, and the hope is to have at least some fair amount of that be open to everybody. At some point it becomes a major, if you're doing major things, you probably have to somehow contribute through a grant or whatever, but there'll be at least some of it that's open completely.
If you're interested in hearing more about Helio Cloud, Brian's going to present on it at our next Telecon on the 28th.
Actually,
nice.
he's not.
Okay, yeah, keep
he's
me
not.
posted.
He's not because he has a medical appointment, but probably he's gonna reschedule with you.
Okay, never mind. He will eventually present on a PyHC Telecon about this. Cool.
You can certainly talk to him anytime you want. Just send an email.
It looks like there's a question in the chat.
Yes, what is the issue with planetary transits?
Sorry, I was muted. Yes. Right. So planetary transits can. So I only mentioned them as something that is removed from the pipeline only from the perspective of a machine learning system, and that's because having these very bright pixels. So these horizontal lines that are very bright, they disrupt the pixel distribution compared to not having planetary transits, which is the data that we want to look at. So either one has a way of sort of removing this, but then filling it in with, let's say, background pixel values. One can do that, but then one introduces sort of artificial data, which wasn't there, or one simply removes those instances. So one potentially, that's also a very nice point that you allude to, I think, is that let's say one can design a more sophisticated neural network that, let's say, has access internally to time periods where there are planetary transits, or is simply using computer vision to itself detect and then maybe not weigh the predictions coming from those images as highly or as much as predictions coming from images without planetary transits. So there is nothing intrinsically wrong. It's just in our approach, and for the machine learning experiments that we were doing, we thought it best to forego having planetary transits.
Last quick question. Stars are also an issue?
There is speckle. There are some speckled images, but that's more to do with the LASCO instrument itself from the cosmic rays that are impinging upon it. In addition to planetary transits, comets can also leave, but they're much rarer in the sense that one would have to have quite a close-up comet right in the path of in the field of view of LASCO and they are harder to detect in a way, because at least they're not simple to detect. Let me say that, because as opposed to planetary transits which have this horizontal bright edge, a comet could have more of a curveball entry. It's more difficult to, and it might be quite the magnitudes, how bright it is might not affect actually pixel distribution at all. So we basically, the cosmic rays creating speckled images are more of an issue than, but that doesn't happen that often either. So I think more in our experience, more it's the planetary transits that play a role.
Gotcha. Thanks.
Yeah,
Awesome.
thank you.
Yeah, I'm excited to have you present on this.
Thank you, Julie. I could say a few more things maybe at the end of the talk, of the presentations, because there were, let's say, comments that are very absolutely correct, that were raised about the intrinsic nature of the images. So maybe 20 seconds, if I may, Julie. Sorry, I'll quickly finish this. Thanks. Okay. What I would say is that, for instance, let's say the in LASCO images, one has this occulter, and this occulter sits on this, let's say, metal. I don't know the technical term for it, but this I forgot, this metal rod, right? So that the interaction of light with that rod can create different kind of patterns that might affect a machine learning system. Our working assumption has been that we don't do any processing on top of the intrinsic images that are at the NASA archives. But when those images are being used, it's also important to keep in mind that the machine learning system that's produced should be able to deal with these kind of nonlinear patterns that come from certain intrinsic features in the images themselves. Also, for instance, the degradation in the EIT instrument that's there. And these are things that are quite high level in terms of the physicality of each of these instruments. But a well-designed machine learning system should be able to deal with these various kind of lurking effects. Okay, I'll stop here.
Thanks, Carl. Yeah,
Thank you, Julie.
Yeah, of course. Yeah, in past conversations with PyHC community members, we've talked about, having the need for machine-ready learning data sets. And so when I came across your tool, I was really excited to have you presented on that. Awesome.
Thank you.
Jenny, yes. Jenny, would you like to bring up the topic you wanted to discuss with the larger group?
Sure, yeah, I guess I'm excited to be here and see you all. I have to preface my question, I guess, that I'm going to ask with saying that I am not a Python user. I'm also not a scientist. I'm a front-end web developer, and I work with space weather data mostly and help make user interfaces for it. So I guess I was thinking, Carl, if the tool is in the cloud, like my role would be to make a user interface to help run the tool and put together the different data sets. Also, that last one, the last point you made about the Coulter's arm or rod or whatever it's called, like that could be a plugin library or something that you could add to your data set so that it's reproducible. So anyway, that is along the lines of what I was going to ask about this community about as well. Is Pylon? Okay, good. I thought that was a Python reference, like a it's not a Python reference, but that would be a good name for the plugin to get rid of the ARM data. But anyway, I just want to talk about, I guess I've been talking to people who use space weather data, and there are certain really fundamental data sets that are used as input to various models that are not standardized. So like you said, that you take the raw data, you don't want to change the data, you want to make it replicable. So I guess I wanted to ask about specifically, so this maybe is very small potatoes, but specifically the F10 radio flux data. And I know that it's taken 3 times a day, and So in the winter, it's at a different time, one of those times than in the summer, because the valley where it's taken is too narrow to have the sun at the later time in the day. So anyway, this is a data set that's used as an input for models. But people, I guess if there's a solar flare or different outliers, that changes the data input. So everybody does their own manipulation of the data to standardize it for their purposes. And so I was just wondering if there is like a standard library for a transformation of that data that people could use, or different libraries that people could use to say like, okay, I use this transformation and it has a name, so that it's replicable in these models, so that we know what inputs people are having. So I can just show an example. I mean, people probably know what I'm talking about, but let me see, I think I have a zillion tabs open, but if I go to the lizard database at, which is one that I know, and I'll go to the newer version that's coming out. And then I hope this, I guess my connection is not so good because I'm sharing, so I should have preloaded this. Oh, it's really bad because someone else in my household is also on a Zoom meeting right now. So I should have plugged into the Ethernet. It should load. Oh yeah, see, great. Maybe I'll turn off my video. Let's see. Let's refresh this. This is not a good, okay, here we go, finally. Okay, data. And then again, that's gonna take a second. And scroll down to Penticton 10.7. And so this has all of the data for all time. So we'll just do the adjusted and plot that. And then you can zoom in and see the variations per day. But anyway, maybe someone wants to jump in here and interrupt me and say, oh yes, we've dealt with this in this way, or, you know, I don't understand what you're talking about, or, you know, that would be a good idea, but it's not important enough or something. I don't know. Anyway, so what, oh, page unresponsive.
Well, I'll just add that, yeah, I found this, you know, Carl's talk was kind of enlightening too. It's a similar sort of a deal where, you know, we could make a new standard data set and then everybody uses that data set, but there's usually a lot of choices to be made on how do you want to process the original data. So generally exactly. a new standard product isn't sufficient, but having a standard algorithm strikes me as being a more, you know, scalable solution. And so kind of like Carl has his published pipeline, you know, could we be publishing these standard algorithms, you know, maybe as part of SunPy or something else. So that's kind of part of how I'm seeing this problem.
Yeah, so here's an example of Penticton data every day. There's 3 readings, and then you can see there's these different outliers, especially if there's a solar event. So on the bottom here, you can see the solar cycles through time over decades. And what you really want is the sort of smoothed version of the data. And so how people do that smoothing varies person to person right now. And it would be nice to have a standard. So like, just like you have a map projection that's called the Mercator projection, or the, you know, whatever projection you choose, you can say, I use this method for this data. But also there might be other data sets. I know there are other data sets that are used over and over again that could use some cleaning or standardization, and everybody does their own approach. So, but yeah, tell me what, as modelers, does everyone use their own approach, or is it more like what Carl has outlined, where there's a standard pipeline or standard algorithms to standardize the data?
I think you may need a simulation community. The CCMC folks would probably be a good place to
yeah. Let's see. Darren?
Right. So someone said iSplat would be a good good place to request standardization algorithms.
Well, I'll speak up as a representative from the HAPI side of things. HAPI is a data server interface, and I think Doug can confirm this, but I think there's a happy interface to the lizard stuff too. And so one thing that you could conceivably do is create sort of happy processing modules or conversions. Take this happy stream and apply the following thing to it and make it available as an equivalent happy stream on the output. So you could publish algorithms that way that could absorb happy data and do something to it. That has not been done yet, but that's something that's super relevant for lots of machine learning things in terms of do something standard to this data.
So it would be like an operation that Happy could do.
Right. Yeah. So that's kind of low hanging fruit. No one proposed that yet, but that could be done where you create kind of standardized set of routines that operate on the standard set of inputs.
Yeah, the big question in my mind, I like a layered approach.
Yeah.
And so where, Carl's stuff, I can see it's kind of the full pipeline. And I'm not sure how easy it would be to adapt, if I wanted to just factor out one layer of that, presumably that kind of thing is doable. But then the question becomes a question of data models, for example. So if and John, you suggested, could be a happy stream, could be this unifying data model. But I'm also curious what other, the data models that SunPy and other HelioPython libraries support. So that way, we could have, some data source comes through some standard interface, some standard format, then we can pipe it into this algorithm, which could pipe it through a standard format. So it becomes a question of standard formats. HDF5 from Carl's stuff sounds great, but it's going to be now, if somebody wants to consume it, they're going to have to, be able to read those HDF5 things. So, how can we, this is a huge problem. I don't know, certainly I can solve it now, but I think it's just an interesting discussion is to think about, and I think Happy has really opened up this idea of this service-oriented architecture and being able to stream stuff. So instead of just downloading files in a specific format, being able to stream data into the actual data structures in your code. So whether it be pandas or whatnot. So maybe pandas could be that common format, for example.
Well, pandas doesn't do well with high dimensional stuff, I don't think. And so there is effort we've been trying to get going for over a year now to have all these different libraries, SunPy, SpacePy. We only had funding to do some of them, but to be able to adapt each other's data models so that if you had Happy, SunPy could absorb it. If you had SunPy time series, then there was an adapter that you could put that behind a Happy server, or SpacePy similar. So I don't want to take up too much time. Russell's got his hand up.
Yeah, Darren, before Russell, you had unmuted for a second. Did you have a comment you wanted to make?
Yeah, I was just going to say from kind of I wear a couple of different hats, but as a model developer, we're not actually trying to do the analysis of this ourselves. We find a source for somebody who's created a smooth timeline of F10.7 to use, and we're ingesting it into our models, right? And so the science of how to create that is not something that an individual modeler will worry about. They'll find somebody who's done it. And so you kind of need to find the specialists who are doing that analysis and maybe talk with them and say, is there a consensus on how to do this? We're finding a place that's already done that analysis and using their expertise to ingest it into our models.
And then that's replicable. Because I guess we're talking about like an API doing it versus the library, but it really comes down to the algorithm, and just that it's an algorithm that is understood and named and can be replicated, whether it's just from the API side or the Python side.
That's a good point. Yeah, that there's an algorithm base, and then you need like a schema of algorithms that everybody accepts, and you can at least say, oh, I use this one. Yeah, that's still hard getting everybody to agree on
but at least they're identifiable. If we can publish the algorithm and be able to have a reference to the algorithm we used, that would be going a long way.
Yeah, because I've asked, is there steps you take? Like first you average them, then you know, whatever. And the researchers I've talked to say, no, there's no agreed upon steps, which is what an algorithm would be. So anyway, Russell, did you want to chime in?
Yes, please go ahead.
Yeah, I just want to let you know about the PySat and PySat space weather package. So PySat is kind of built exactly for this type of thing, which is getting data down from a variety of sources, but also processing the data in custom ways. So you can actually just write the algorithm and distribute it as part of, PySat, or your own module is actually built on, people making their own data modules and processing. So you can refer people to that. And PySat works with pandas and Xarray. So it's kind of built on existing data formats, but it's really built around custom processing and being able to share that processing with others and easily and apply given processing to a variety of different data sets. So you just might.
So there could be like for example, a Penticton or F107 module of PySat, not module, but whatever library of PySat that would do that transformation for you. That would be open source and identifiable.
That's correct. Like right now, we actually offer F107 through PySat Space Weather from LASP, actually. So I don't know if it's going through this lizard.
Yeah, I don't know if it's been standardized, possibly, but I doubt it.
That's part of the thing, because we work on Lizard here at LASP, and I don't really, I don't even know what F107 we're providing right now. We used to get it from NGDC. They stopped providing their product, so we've been going straight to Penticton. But then we've got scientists who are using it, and they have their special processing they use, and so that's kind of what got this question spinning. Is, well, we've got this new F107 as an intermediate product for some other project. Well, how could we share this, because it's very well vetted? So how can we share this alternative algorithm for generating these things? And I also want to emphasize. I'd be curious
what other. Oh, go ahead. Yeah.
I just emphasize one other point that I think was kind of made, is the distinction between algorithm and implementation. So I definitely like the idea of being able to define the algorithm in a agnostic way, and then there could be a reference implementation of the algorithm in a particular Python library. So that kind of addresses the issue, is like, we don't all have to use the same library. We just need to be able to use the same algorithm.
Really good point. We've unfortunately run up to the end of this Telecon time, but Jenny, we do have a PyHC group on Helionauts. Maybe if you want to post about this on there, we could have some more discussion, get some more perspectives on that. Just wanted to point that out. But yeah, thanks to everyone for coming on. Thanks again to Carl for presenting and Jenny for bringing up this discussion topic. Our next Telecon will be in 2 weeks, same time, same place. Just note that there's now been, daylight saving time, so it's 15 UTC, not 16. And we'll have an update on Pan-Helio from Alec Engel. Thanks, everyone.
Yeah, thank you. See you next time.